climate modeling, like an introduction to climate modeling, and then reanalysis, and then I'll hand it over to Ziqi, who will talk about emulation with machine learning of climate system. I'll try sharing my screen and check it. Everything works okay.
Yep.
Do you see my full screen? Everything looks good, or should I swap display?
Could try to swap. It's a little smaller.
Okay.
Yeah.
How about now?
Yeah,
Is
that's
it full
better.
screen?
Yes, that's better. Thank you.
Yeah. Yeah, a lot of us in iHarp work on data science and harnessing data science for polar climate understanding, improving prediction. Today, our introduction will be more on like what is a climate model, how do you formulate a climate model, and what are some of the uses of the climate model. It's a very broad introduction and like just 15 minutes. So feel free to stop either Ziqi or me anytime to ask questions. Yeah, I'll give an introduction to climate modeling, and then I'll talk about reanalysis, which involves blending numerical models with observations and data from the real world to get a best estimate of the Earth system. I'm Aneesh Subramanian. I'm a faculty at CU Boulder and one of the co-PIs in iHarp. My group here, we work on understanding climate processes better within our Earth system, from the tropical to polar regions, ocean atmosphere, land ice, and the cryosphere as well. And we also work on prediction and predictability. How do we improve the prediction of the Earth system, and how do we understand fundamental predictability of the Earth system? And Ziqi, I think Ziqi will introduce himself when we start on the climate emulation. But maybe Ziqi, you can introduce yourself now, if that's.
Hi everyone, I'm Ziqi. I'm a Ph.D. student in Aneesh group, and I'm going to start my 5th year. My study focus on ice sheet climate interactions, especially like surface melt, like the processes happening at the ice sheet surface. Yeah, thank you.
Yeah, so if you think of what a climate model is, these are some very simple definitions of climate model. Even independent of a climate model, think of what a model itself is. A model is our representation of what we understand of the real world, right? So models are used for learning about the real world, and learning takes place. If you think of a kid like in this cartoon, like Calvin, um, making a model of like a fort or some part of the real world. Similarly, learning takes place in the construction of reality using blocks or using smaller parts to build the full picture of what we think the reality is. And we also, once we do that, we can also manipulate the model. So for instance, if Calvin is building um, the sand castle here, and then he goes and destroys it with a meteor, right? That's like a manipulation of the model, even if in the real world, and it doesn't happen immediately, but you can imagine what might happen if the meteor in Calvin's hand crashes into the sand castle. That it can destroy the structure. So similarly, climate models are idealized representations of the complicated and complex Earth system that we live in. There are many different components, as we call them in climate sciences. The atmosphere, for instance, is one component. The ocean, the cryosphere, which is land ice or sea ice, is another component of the Earth system. So we build models mathematical models based on physical principles or chemistry of the Earth system. And we then put them all together to build a full Earth system. And I'll talk about that in the next few slides. And then the other part to building a model is that it always involves some approximation to what is happening in the real world. So we always tend to either ignore or approximate some of the processes in our Earth system by some simpler representation of them. And then we build the model from there, and then we can add complexity to the system as we understand the Earth system more and more. So it's thinking of like a child's Lego construction. You can think of it's there's like a basic building block to the Lego construction, but then like people can build like highly detailed representation of buildings with the same Lego, right? Like a child might build just like a simple cuboid shaped building, but then people have actually rebuilt like a stadium or like a New York skyscraper with the same Lego blocks. So you can think of the climate model also something similar, where we can start from a very simple representation of the climate system and build up into complexity. The fundamental building blocks of the climate system are differential equations. So they are mathematical equations that represent the physical laws and the chemistry that govern the dynamics and the thermodynamics and chemistry of the Earth system. And in climate modeling world, we call it to run a climate model. By running a climate model, what I mean is to integrate these equations in time. And the equations are represented on a three-dimensional grid. You have the same equations at every grid cell throughout the globe that represent the fluid dynamical motions, or it can represent the thermodynamics that governs like temperature or humidity or salinity in the ocean. The same equations are solved at every grid cell, and then each grid cell communicates with its neighbors to pass information at every time step. Like I was saying in the previous slide, there's a very simple, minimalistic definition of a climate model. And the most simple definition is what's called as a zero-dimensional climate model, which is essentially just representing how much energy comes into the Earth system from space and how much energy is leaving the Earth system as it radiates heat out. And the net effect of that incoming minus outgoing energy is what determines the average surface temperature of the Earth. So you can build this very simple climate model with one equation that just represents how much incoming radiation is trapped within the Earth system and how much of it is radiated back to space. And the amount of radiation that is trapped in the Earth system determines what's the temperature of the Earth's surface at which it radiates. I'll not go into the math of this simple climate model due to time, but I'm happy to talk later about this if required. So what's a global coupled climate model? This is a schematic. Again, I cannot see if there are questions on the chat or if hands are raised. So Josephine or anyone
I'll
else,
let you
feel
know.
free. Okay,
Yeah, sure.
thanks. So this is a schematic of a global atmospheric model where the atmosphere in the Earth from the surface where we live all the way up to like, it can be up to 30 kilometers or all the way to the top of the atmosphere, which is like 150 kilometers from the surface or higher. It's divided into cube grids, so grid cells. And each grid cell is solving these fluid dynamical equations called Navier-Stokes equations to resolve how wind flows around. It's also solving physics equations such as radiation. How does radiation interact with clouds? Cloud physics equations that solve for how moisture in the grid cell can become liquid water in the clouds, and then they can precipitate out onto the land surface. There's like a lot of complexity to the full Earth system, but the fundamental idea is that you have these mathematical equations that define physical laws of the Earth system, and they are solved on these grids. An example is the National Center for Atmospheric Research, NCAR, which is based here in Boulder, Colorado. They have developed one of the best community climate models that is open source, and have one of the largest user bases in the world. Their model is called the Community Earth System Model, or CESM to be short. It's a coupled ocean, atmosphere, land and sea ice model. And you can configure this model in many different resolutions. The typical time step, which is how you integrate the numerical differential equation forward in time, is about 30 minutes. The atmospheric column is divided into 30 atmosphere levels by default. You can increase or decrease that if you would like to do other experiments. The ocean has 60 vertical levels, and then the land surface has 15 layers. So at 1 degree resolution, which is the default climate resolution, there are about 5 million grid boxes that cover the entire Earth. And you're solving these differential equations as well as physics and thermodynamics equations. The amount of computer code written to do this is about 1.5 million lines of computer code. And you're just solving mathematical equations which lead to what are called emergent features. Like, for instance, the seasons like summer, winter, they are not actually encoded in those equations, right? They just come about because of solving these equations on a global grid with changes in solar radiation, changes in sea ice and other properties. Similarly, El Nino, La Nina is another emergent property. Global warming is another emergent property that is not written into the equations, but because the equations follow the physical laws, you get these emergent features in the solution. Yeah, this is a movie. Maybe in the interest of time, I'll try to speed it up, but it's just showing examples of what outputs from climate models can look like. It's showing how integrated precipitable water, which is amount of water in the atmospheric column, moves around on a day-by-day basis. You see most of the water trapped in the tropics, but then there are times when these narrow tendrils of water can stretch out into the mid-latitude or even into the polar regions or onto Greenland. And they can bring moisture as well as warm air into these higher latitude regions. So this is like an output from just solving those equations, right, on a numerical grid. And then on the bottom is showing a future climate simulation of the same. One thing that jumps out is in a warmer climate in the future, you have a lot more moisture stored in the atmosphere. This comes from a fundamental physics law that warmer air can hold more water vapor. And you also can potentially see these more intense storms like extratropical cyclones or hurricanes that emerge from the solution of the climate model. And then the other really important is the same slide. So yeah, other really important application of climate models is to project into the future and look at how future climate could look like. And one thing that's been seen in every climate model is that with increased greenhouse gases, you see a warmer world with temperature almost everywhere around the globe increasing significantly. So this is from, I think, close to a decade ago, a simulation showing how much warming we would get by the end of the century. And yeah, the actual simulation, I have a YouTube link which you can look up later, but it goes from the 1850 and it shows the temperature change as a function of space and time around the globe over a 150-year period. The historical period matches observations pretty well, and then you can also look at future temperature changes into the end of the century. So how are climate models used? They're used to test hypotheses and to provide predictions. So if you have a scientific hypothesis of something related to climate, you can test that with climate models. And you can also use climate models to do predictions out to 10 years, out to a season, or all the way out to the end of the century. There's a great quote that I really like by George Box, who said, all models are wrong because of what we said in the first slide, that there's always some approximation or something that is being ignored. But some models are useful because they help us understand the world better and help improve both our understanding as well as predicting the real world. There's another example of what climate models are used for and how they can match observations in the Arctic as central to iHarp science. We know that the Arctic sea ice has been declining over the many decades because of warmer surface temperatures in the Arctic. And people have used climate models to then project forward on seeing when the Arctic would be completely ice-free in the summer months. And the consensus is about mid-century, we would start seeing an ice-free Arctic with no ice in summer, right? Yeah, so there's a lot of complexity to climate models. Like I mentioned, there are physical equations that are solved on these grid cells. The other part of the climate models is each grid cell is about 1 degree by 1 degree. So that's like 100 kilometers by 100 kilometer on average in the tropics or mid-latitude. And that's a large area, right? If you look out of your window, for instance, you wouldn't be able to look 100 kilometers from where you are. So there's a lot of processes that are happening subgrid scale, as we call it in climate modeling, or within that 100 kilometer by 100 kilometer grid, there are like different clouds that can exist. There is different vegetation, different land processes, or even ocean processes. So all of those subgrid scale processes, small scale processes, are then parameterized or represented with simpler physical equations. And then they are solved at every time step, and their output then feeds into the larger global climate model. And these parameterizations are built on our understanding of processes based on observations, as well as people run highly detailed models to represent these fine scale processes, and they use knowledge from these fine scale models to then build climate models. So just to introduce the structure of the climate model, a fully coupled climate model, it can have a atmospheric model, a ocean model, land model, sea ice, land ice, which is critical to the polar regions, that is central to iHarp. It can have a river model as well. And the atmosphere can have chemistry, the ocean can have biogeochemistry, which are separate modules that are coupled into the climate model. And the arrow denotes exchange of information by this coupler, which is what is bringing all these components of the Earth system together. And it exchanges information between the components. So the atmosphere, for instance, is exchanging energy with the ocean or the sea ice or land ice. It's exchanging carbon, water as well with precipitation. So all of that is exchanged by the coupler in a climate model. And then the other part of climate modeling is looking at what would happen in the future if you have some kind of external forcing to the system. So typically external forcings to the system are greenhouse gases or anthropogenic aerosols, or if you have volcanic eruptions that are not like part of this Earth system model. So they are prescribed, or they are like put into the climate models as external forcing. And then we can look at how the climate models respond to this external forcing. So if you can think of it as like you have the Earth system, think of it as a drum. And then if you take a drumstick and you hit the drum with the drumstick can be thought of as external forcing. And then how does the drum respond to produce sound is what the response of the Earth system would be. Right? Yeah, so there are many purposes to climate modeling, including these that I've listed: scientific and mechanistic understanding of past observed events, as well as changes to the past climate, studying future climate change, studying variability within the climate system, as well as predictions. So we can do predictions from like sub-seasonal timescale out to multi-decadal timescale with climate models. And these then provide information to the society that is actionable, right, that people can make decisions on. Yeah, and climate modeling is a key information source, or it's a key basis for the IPCC reports that have informed on future climate change in our Earth system. It's a virtual laboratory to study many different processes within our Earth system and how these processes interact, and they can also change in the future. Yeah, I was going to do reanalysis next, and then hand it over to Ziqi. Unless if there are any burning questions on climate model that is quick, I can answer it now, or we can take questions in the end.
Thank you, Dr. Aneesh. Can I go?
Yeah, sure, Malloy.
So, like for developing a climate model, what do you think? Like, how many years we need generally, like actually?
Yeah, I mean, to develop like a numerical climate model that exists currently, it takes like decades and like many scientists, right? Like for instance, the NCAR CESM that I showed, the first versions of the model, which was just the atmosphere, was like in the 1970s, 1960s and 70s. The first fully coupled ocean atmosphere sea ice was in the 1980s and 90s. They were developed. The land ice model was in the past decade or so. They've started like testing it, and now they're coupling it to the full Earth system, like the Greenland ice sheet or the Antarctic ice sheet, right? And there are like more than 30 or 40 scientists at NCAR who are involved every day building and testing the climate model. But also getting input from the larger community, which is like hundreds of scientists around the world, like within US and outside.
And like, is there any way to replicate the climate model with data science machine learning?
Yeah,
Like,
there is, and which is what Ziqi's talk will be today. The third part of our talk will be about emulating climate
okay,
with machine learning. Right?
okay. That will reduce
People have
cost,
had,
right? That will
yeah,
reduce.
exactly, yeah,
Okay.
that would reduce the time. Like for weather, there's been a huge success. Like weather emulators over the last 5 years have like already beaten the existing numerical weather models that took like 3 decades or 4 decades to develop. Right?
Okay,
Yeah.
thank you for the information.
Okay, thanks.
I have a question too.
Yeah, go ahead.
So when you spoke about the fully coupled climate model, visualize the complexity of all the elements that are being, integrated here. And as you've mentioned, when you to Maloy's question, is you've said there's so many. Obviously, they started with an atmospheric model, and they've been gradually, adding all these other elements to it. Now, with research scientists like yourself, you're also individually doing a lot of modeling on the side, and you probably are focused on the either atmospheric side, maybe coupled with another. How much of this is integrated into something like CSM, for example? Because you guys are studying different things. They do have their teams over there, but how much of this, because what you're also doing is important, so how much does it contribute towards that? Yeah.
Yeah, it's a great question. And just as an example, like Ziqi, who his first project in grad school was to work with the land ice model coupled with a higher resolution atmospheric model in CESM. And Ziqi was working closely with like the people who developed the climate model in NCAR to test some of their runs to get like a better understanding of like if you have a higher resolution in the atmosphere, what's the impact on the Greenland ice sheet. And that then goes back as feedback to the model developers, right? Saying like these are the things we observe um, when you run a higher resolution atmospheric model with the ice sheet model um, uh, below it. So yeah, like there are people who work closely with and collaborate with the model developers, and that's one direct way to impact the model development. But otherwise too, there are these projects called Climate Model Intercomparison Projects, CMEP, where um, they may not be interacting with any of the model developers at NCAR, but they still evaluate NCAR's climate model and compare it to observations and compare it to other climate models. And their evaluations will then help inform the scientists at NCAR about, okay, their model is not doing well in some physics processes, it's doing well in something else. How do we tackle those physics processes that it's not doing well and improve that? Yeah.
Thank you. Dr. Shashi has a question.
Yeah.
Oh, I can read it out. Okay.
Oh, okay,
So
sure.
So it says the plots in this slide titled "The Context" appear to show a mean and uncertainty band. How is uncertainty estimated and quantified?
Yeah, so here the uncertainty is estimated by what's called as ensembles. So the climate model, you can do one integration starting from some initial condition, but you can also do a integration where you perturb the initial conditions by a small amount. Because our Earth system is chaotic, it leads to a divergence of the solution quite rapidly because of a chaotic system. So in that sense, people add perturbations to the initial conditions of the climate model, and they then run like many simulations of these. And then in this specific case, this is IPCC, where they have multiple models also, which have different physics, different representation of the dynamics as well. So that adds to the uncertainty as well. So you have multi-model uncertainty because of different ways of representing physics and thermodynamics in the climate model. But each model with the exact same physics can still run an ensemble to get to that natural variability, which is a part of the uncertainty as well. I can't see the chat. Yeah.
Yeah, he has a follow-up questions. So do the global climate models model ice age? When is the next one, and how does it interact with recent warming?
Yeah, it's a great question. I don't know when the next one is projected, Shashi, but they do, yeah, like the paleoclimate simulations, which run at a very coarse resolution, they do simulate the ice age, the last glacial maxima, and there was also like a little ice age, like a couple of centuries ago, and people do simulate those little ice ages as well, where I think the ice had come down into Europe, like middle of Europe as well. So they can represent ice ages, but they are approximations because they are run at very coarse resolution with less physics being resolved as well.
Great. Thank you. Thank you.
Thanks. Yeah, so maybe in the interest of time, I did talk about climate change and the use of climate models for climate change, which is what this slide is about as well. And then in terms of climate change, people look at surface temperature and how surface temperature changes and projections to the future, how heat content in the ocean changes and how does that change in the future. How does sea ice and sea ice area change, like I discussed in the slide previously, as well as precipitation and how does rainfall change in the future, where you have more moisture in the air, and how does that relate to precipitation. So the role of reanalysis is to get the best possible reconstruction of the past, right? Like reanalysis cannot be used by itself to study the future, but what reanalysis can do is to reconstruct the past the best possible way by combining a climate model or a weather model, which solve those equations that I talked about, with observations, with data from the real world. So you're taking modern observing systems such as satellites or aircrafts, balloon observations. You can also take historical data records from like ship logbooks or proxy data from tree rings, and then use all those observations of the real world, blend it into the climate model, which I'll talk about how that is done in a couple of slides, and then reconstruct what the past climate looked like. This is just a plot showing how much observations we had. Like until like the mid 20th century, we did not have much observations, right? And then since about 1930s and 40s, there's more and more observations. The first satellites came through in 1970s, and then there's been like a lot more observations from satellite records. So the role of reanalysis is to describe the dynamics of the climate system in the past, and also how observations relate to the model variables. So reanalysis can assimilate many different types of observations into the model. And for those who are not familiar with what assimilation is, I have 2 slides on that in a couple of slides. They produce estimates of all variables that are solved in those model equations that I talked about. And they also ensure that these variables are physically consistent with each other. Because the observations are sparse, like you have observations only in some places and only at some times, they may not be just looking at observations, you don't get a physically consistent view of the world. But when you blend them into the dynamical models, you can then construct a physically consistent reproduction of the Earth system's state. And they produce output on regular space and time grids. Some of the limitations is that, like I talked about, climate models are limited, weather and climate models. So those limitations are built into the reanalysis as well. And observations are also limited. We don't have observations everywhere all the time, only some observations in some places, and some of the observations are also uncertain. So all of that adds approximations or caveats to reanalysis. So there's an animation showing how many observations we had from the 1940s. So most of the observations were either close to the surface, or there were a few in the upper atmosphere because of balloon launches from land or from ship-based observations. And then as we got into the 1960s, there were more variables, like humidity was another variable that was added because we had sensors for humidity. 1970, the first satellites to observe ozone and infrared radiance came online. You started getting surface pressure observations as well in the 1970s over the ocean from ships and other buoy deployments. And then in the 1990s, you had a lot more launches of satellites that observed sea surface height, that observed surface wind, soil moisture, atmospheric motion winds from observing clouds, snow cover in the 2000s, and then more observations came online in the 2000s. Right? All of these observations are then assimilated into this product called ERA5, which is the European Center's Reanalysis 5th generation, which is currently the best available reanalysis. And the ability to reconstruct unobserved variables is really good in the climate model because we're solving these dynamical and physical equations. This is just an example from a paper in 2009 where they used just the surface pressure observations. So observations just at the surface and look at 500 millibar, which is about 5 kilometers from the surface up in the atmosphere. What's the pressure field look like? And then this is the same 500 millibar reconstruction from a complete observing system that has observations in the upper atmosphere as well, right? And what we see, at least on the large scale, is that it's a really good representation, even though on the right-hand side, you're assimilating only the surface observations, that still helps constrain the upper atmosphere's field as well. There are many different types of reanalysis. There are global reanalysis. There are regional reanalysis. There's one called CARA, just in the Arctic region. And there are also reanalysis for different components of the Earth system. ERA5 that I mentioned is just for the atmosphere. Similarly, there are reanalysis for the ocean, for sea ice, for land surface processes. And there are also different time periods of these reanalysis. There is modern reanalysis, that is the best reconstruction of the Earth system that assimilates modern observations, satellite, aircraft, and all of those. There are also centennial or paleo reanalysis that go back hundreds or thousands of years, but they are poorly constrained because of the lack of observations that far long. The idea of reanalysis is you integrate the model forward in time, and whenever you have observations, you compare the model to observation, and then you can correct the model towards the observation using different approaches. The two main approaches, which I don't have time today to go into, one of them is called variational analysis, which is minimizing the distance, the root mean square error distance between the observation and the model. And another approach is called an ensemble approach, the ensemble Kalman filter approach, which is trying to get the best linear estimation between the model trajectory and the observed trajectory. So in this case, you're running the model as an ensemble, and then the observation, there is uncertainty added to the observation, and then you're trying to optimize between the two distributions, between the observed distribution and the model distribution. Yeah, I think I should let Ziqi go now so that we have 5-10 minutes for Q&A. But there's differences between reanalysis and forecasts, which reanalysis can go back in time and has the benefit of looking in the past to correct the past and future to correct the present. Whereas if you're doing an operational weather prediction, you only have the current and the past observations to predict the future. Yeah, I'll leave these on. These are some of the benefits of reanalysis and some of this special challenges to old observations. But yeah, I think in the interest of time, I'll skip these slides. You can go back and look at these again, and I'm happy to chat offline with anyone who's interested. There's been changes to observing system. There have been improvements to the data assimilation algorithms as well. And then there's like corrections to observations that also help improve reanalysis. And then in the modern reanalysis, they also produce uncertainty that, like Shashi was asking about uncertainty to model projections. Now they also produce uncertainty to reanalysis because observations have uncertainty, models have uncertainty. So then when you do the ensemble data assimilation, you get an uncertainty from the ensemble that goes into the assimilation. And then reanalysis is very useful societally as well. It helps inform about the recent past. Like people look at extreme weather in reanalysis because it's the best three-dimensional representation of the weather evolution. In the Arctic region, in the polar regions, there's like CARA, which is a regional analysis, which many of us in iHarp have used as well. It's a huge production. There's 1 petabyte of data that is downloaded on a weekly basis, 250,000 users around the globe. And just the European Center is a major distributor of reanalysis data. Yeah, final thought, reanalysis is indispensable for our research of earth sciences and also climate services. It's one of the most cited data sets in scientific literature, and it provides like fundamental training data for machine learning applications. And then, yeah, just one transition slide to Ziqi's talk. This is an article about Jensen Huang, who was the CEO of NVIDIA, who talks about how AI can then help improve prediction of extreme weather by producing many realizations. Because, like Malloy was asking, it's computationally much more efficient to run AI models if they are skillful. And then Ziqi will talk about model emulation with machine learning AI next, which talks about that problem. I see Shashi has his hand raised. Did you have another question, Shashi? Or?
Oh, no, I should lower it. I think you
Okay.
heard both of them. Thank you.
Can you see my screen?
Yeah, I can see.
Yeah, okay. So yeah, I'm going to continue to talk about climate emulations, and I will focus on polar studies, but the emulations are not limited to polar regions. The emulator is a statistical or machine learning model that trained to approximate the output of a physical model, like the climate model. And you may know this as a surrogate model, which is similar in data science or computer science. And as shown in this figure, that unlike climate models, like it contains many different components and processes. The emulator is trained from the input variable and to directly approximate to emulate the output variable, and which can be much lightweight and save the computational cost. So because as Aneesh already mentioned that emulator can be much faster than traditional like physical climate simulations. So it allows thousands of example runs, and then you can do, it's easier to do uncertainty quantification and sensitivity tags. And also it enables parameter tuning and optimizations. And then combined with causal inference or feature attribution techniques, it can also improve the interpretability. And this is also is a bridge between data science and also climate science. And there are like different kinds of emulators, from the most commonly like statistical models like simple regression and Gaussian processes, to nowadays popular machine learning models like neural nets, convolutional neural network, graph neural network, and transformers. And there could also be hybrid approaches like combining physical principles with machine learning methods, and also can combine with causal inference. For example, like it can include physical like conservation laws, like conservation of mass or energy, into the emulator. And there are, because of this fast development of AI, so there has been a growing applications of emulators in climate science and also polar studies. So for example, it can be applied in different topics in the polar regions like sea ice, glacier, ice sheet, and snow, and also sea level change. And also Aneesh mentioned about this machine learning weather forecast models. Although they are not commonly like called a emulator, but their method is similar to the emulator, like this applied to different components. And I think also it can be applied, like combined with climate models, like replace part of the climate model, like parameterization, and so it can, sometimes it can better represent the precise, and also it can speed up the simulation. And next I will use two examples to illustrate the application of emulators in polar studies. So the first one is an example using building an emulator to emulate Antarctic ice shelf firn air content. And the firn is a medium state between fresh snow and ice. It's compressed because of gravity, but is still not formed as ice, and it still has some air content within itself. And firn air content is an indicator of the meltwater retaining ability of firn. So nowadays, most of the Antarctic meltwater is retained in firn, but as climate warms and more meltwater refreeze in the firn layers, this firn the air content will reduce, and it cannot further retain meltwater. So like shown in the right plot, that it can form melt pond or at the surface, and then which can drain into the fractures and cause ice shelf collapse into the ocean. And in this study, Devon, who is a previous member in our group, they building an emulator to emulate the firn air content over Antarctic ice shelves. So traditionally, people use physical models like this is a firn model called snowpack, which is a column model that simulates different layers of firn and snow, and also simulates many processes within the firn. And so this model can be expensive to run, especially when you want to run for a long time, like hundreds of years. So by building this emulator, it speeds up this simulation, and also it only takes a few commonly available variables from CSM2. And after building trained, this emulator is also applied to ERA5, like the Reanalysis data, and also SIMIP6 simulations from other models and different future scenarios. So it by doing this, they build an example of the firm air content. And this is just one result plot from their paper showing this map shows the firm air content they emulate over different regions, and panel B shows their changes. Panel C and D just show the future changes of firm air content over different regions, and the first one is the Arctic Peninsula here, and the second one is the Roni Future ice shelf. So by using this example created by the emulator, we can see that this firm air content is going to be highly impacted, like reduced to the end of this century in the Arctic Peninsula, but in the Roni Future ice shelf is not really impacted like to the end of this century. And another example is this is my last PhD project, and we are trying to build a 2D emulator to emulate Greenland surface melt. The previous example I just showed is a 1D emulator. It's just the input variable is they are within the same grid box, and they try to they emulate the variable firm air extent of the same grid box. But because we think that the surface melt of the ice sheet is not only impacted by the local variables, but also from remote regions, so we want to build this 2D emulator, which also use CSM2 simulations to train and evaluate. And the method we use is kind of graph transformer. It combines graph neural net, which taking with account for the neighboring nodes, and also attention mechanism that also account for impact from remote places. We use 10 members of the simulation for training and last member for the evaluation, and this is just this just shows the structure of our emulator. This plot shows the example of the emulator's result. So in the left, the first panel shows the melt from the CSM2 model, and the second panel shows the prediction by the emulator. This is an example of the year 2014. And the third panel shows their differences, and the last one is the percentage of these differences. So by comparing the first two panels, we can see the emulator can get the general spatial pattern of surface melt. But when looking at the differences, we can tell that there are still underestimation of the large melt values over the ice sheet margins. And over these regions, the differences is like 20%. So we are still need to improve this emulator. And I think this is a common issue of some emulators, that it overly smoothing some of the sharp gradient of the field. And so there are some open questions that are being researched, like how to embed physical constraints in the machine learning emulators, and how to quantify the uncertainty, and also how to improve the emulators explainability. And I think this is a topic that offers a lot of opportunities for collaborations between climate scientists and data scientists, machine learning experts. So to summary, climate emulators offers faster, broader, and more interpretable climate explorations. But emulator is not, most people believe that emulator is not going to replace climate simulations because, but as a complement to simulations, because the climate models are built of the decades of accumulation, decades of the understanding of the physical system is a foundation of our understanding. And I think we also need climate models to provide data to train emulators. And yeah, that's all from me today. Happy to answer any questions.
Okay, thank you so much. Behroz, because of time, we'll just dive in. Behroz, question, please.
Yeah, I have a question like which annotated data set are you using for the emulator for Greenland ice sheet, and is the annotated data set is manually annotated or through automated techniques? And if it's through automated techniques, then which techniques are most suitable and most reliable for the training of the emulator?
So do you ask about the data for training and also the method?
Yeah.
Yeah. So the data is from historical simulations of the CSM2 climate model, and the method I use is a graph transformer. So it's I combine layers of graph neural network and that called gated GCN, and also attention mechanism called performer. So I have tried like different kinds of combination of the layers, but I haven't compared with other.
So
Yeah.
actually he is asking about the data preprocessing, right?
Oh,
Not I think not not your
Yeah.
model. Like you
Oh,
used
sorry.
some training data where maybe you annotated something, but so far I understand for this one maybe you didn't use any annotated data. It is maybe self-supervised model, right?
Yes. So the training data is directly from CSM2 output. What I did is just to define the region of interest and then use the variable as input to the emulator.
So is it like you used for example 5 variables and you using those variables you predicted some future value like this?
Not future value. So so here the emulator just use like 5 or 11 input variable at the of this time step to emulate the melt at the same time step. So it doesn't predict future time steps.
Oh, that's okay. So that means using these input variables, you are trying to emulate another variable at the same time step.
Same
Okay.
time, yes, yeah.
So yeah, that was Behro's question, like if you are annotating something or not. So it's not like like annotation or something. It's like you used 5 or 10 time series to predict another time series.
Yeah.
Yeah, thank you.
Okay, thank you for clarification.
There's one question in the chat, quick. So your slide mentions that you have multiple kinds of emulators like regression, deep neural networks, and so on. What kind of emulator was explored in your work?
In this work, I guess.
Yeah. So actually you can skip that. Your slide mentioned GNN. You can look at the next question. Why GNN instead of CNN or IT plus attention? Yeah.
Oh, So one consideration is that the CNN can be can be applied to latitude longitude grid. Just so this what is called this regular latitude longitude grid. But in the later stage, I also want to apply this emulator to irregular grid, like not latitude longitude, but so they don't have a uniform like grade like neighbors. So yeah, that's one consideration.
Okay. One question might be a little silly question. So as a machine learning expert, if one doesn't consider the physical model, right, in such complex physical environments, would they be going in blind, for lack of a better word, to come up with, a machine learning model of these complex systems? How much do they need this physical model to do the emulator versus someone just getting, data and then starting to build their own machine learning, predicting model or something like that? I guess I'm trying to understand. Yeah.
Yeah, I think that's a very good question, and I'm not sure like how much is needed to build the emulator. Maybe Aneesh, do you know? Like,
How much computation is involved?
Not really, maybe not even just say computation, but trying to really validate. Yes, you have the physical model, but then you're building an emulator, which is pretty much you need to understand the physical model and then have a machine learning, model built on top of that or to replicate it. So if as a machine learning expert, could they do away with a physical model and still achieve a certain level of accuracy and understanding some of these complex processes?
No, yeah, that's a good question. I don't have a full answer. I mean, the example that I can think of is like a weather emulator, right? Like GraphCast, for instance, which is a Google's weather prediction model. They, like the core developers of that model are computer scientists who are not really trained in like earth sciences or weather research. They do collaborate with weather research to understand like the reanalysis data set and what variables are of interest in prediction. But the fundamental machine learning model, like it does not need to know the physics for the weather prediction problem. But then when weather scientists have looked at the output of these GraphCast or these weather emulators, we see that there are limitations. They don't really produce the chaos in the system, like small errors that we know in numerical models can lead to large errors in weather prediction. These machine learning models don't reproduce those. And on the climate side, like people are now developing climate emulators where they have to actually put in some of the physical constraints, like conserving energy in the system or conserving momentum. So there are physical laws that can help inform the machine learning models as well. Right?
Okay, thank you. All right. So we're 5 minutes after. We really appreciate Dr. Aneesh Subramanian and Ziqi for what you've shared. It's very, very insightful. I never had a reanalysis, but didn't even know what it meant. So thank you, at least, for sharing a lot of that. And then the emulators, I had to Google the difference in emulators and simulators. So it's really been, extremely knowledgeable. We will share the recording with folks, and if people have follow-up questions, please reach out to them. Thank you so much for your time.
Thank you.
Thank you, Dr. Aneesh. Thank you, Dr. Josephine.
Thank you for the presentation.
Thanks all. Thanks, Ziqi. Thanks, Josephine. Bye.
Bye-bye.